Good morning, everyone. It's now nearly 4 a.m. on the 29th of October, September 2025, by the way, just in case. Right. I have been into the design and just wanted to talk about the item I just received today. The Omap design that I've been talking about and designing and going through all bits and pieces in the past. So great. I've got the box received from JLC, which I'm going to open up, unbox now, and just show you the contents. I've not even looked at it yet. Just wanted to also kind of discuss my experience with JLC so far. JLCPCB is my number one basically for designing things, well, making boards basically. But this time I wanted to try the PCBA, which is the assembled PCB section. And unfortunately, my experience hasn't been great on that. I mean, they're okay, they're good, but they're not. I think there are a lot for them to kind of enhance or learn from, or make things better. Hopefully, at some point. So, in essence, what the experience was basically is this. I started design in July, or since I submitted to them in July, roughly around July, maybe June or July, I can't remember. And now nearly November. The problem is we had a lot of back and forth emails, and mainly the concern was when I pay for testing and then they say, oh, all thumbs up, all good, everything looks fine, we're happy with the design, we're happy with everything, blah, 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 blah. It then goes into the thing. Then they come back and say, "Please pay." I go and pay. We're talking about not cheap, thousands of dollars and pounds. So I go and pay, and then 2 weeks later, or a week or two later, they come back saying, "Actually, we identified now. This chip doesn't fit on that thing on your board, even though the board and the chip is by them. It's fine." So I go back and then take it away and then try to redesign. Or look into my design and say, yeah, okay, fine. Let's change this from 0402 to 0603, for example. During that period, I had to also purchase additional items that they don't really have. Things like, for example, an Omap chip or an SD-RAM chip or something like that, whereas they don't have it on, LCSC, which is their main source or provider. So I have to go to another process called the global sourcing, which is fine. I then pay for, say, 5 Omap chips because I'm making 5 Omap boards, and 5 SD-RAMs because of the same thing, etc., etc. Then I go back, go into the... I try to reselect and then say, okay, now I've changed the item that you want me to change, and I now need to place it back. I said, no, you can't do that. You have to delete this whole thing and restart from scratch. So I have to resubmit the design one more time. It's a lengthy process. So I resubmit, get it done, and then I add the ones. The default was like capacitors and resistors and all that kind of stuff. But while I'm trying to add my own parts that I from global sourcing, they come back saying, sorry, can't do that because they are locked for the previous design. It's like, why is that locked? And then they have to release. What happens is they have to release the whole thing again, release everything, and I have to kind of redesign, resubmit my Gerber files and then PCBs and all that kind of stuff. So resubmit the whole thing, which is a lengthy process. Then after I submit, after I kind of try to, then they come back opening. Okay, now can you please place match the parts up? So I have to go in, and this is the other problem that really boils my noodles, so to speak, is where I try to select my, say, 5 Omap chips or 5 oscillators, for example. Then even though my each board required 2 oscillators, for example, I have 10 in my already purchased personally thing before they place them on, and I try to select them and say, sorry, you can't do that because your board needs more. So no, it doesn't. My design needs only, so I got 5 boards times 2 oscillators. That should be 10 parts altogether. And they said, no, you need 15. It's like, why do I need 15? And then they're like, well, we placed 5 items for our faults. And it's like, well, if it's your fault, why should I be paying for them? So anyway, that went escalated, and they wanted to, okay, we're just going to do exception for you. Now, you're not going to charge you for that, but just bear in mind, if you place 100 resistor on the board, we charge you for 120, because 20 of them are going to be wasted. We think it's it's going to be a tolerance or something. So I'm thinking it's became a more expensive design than me managing. So my previous videos, I've probably seen them. I decided to buy a pick and place machine during that process, and just to ease this up, because it's much easier, much better. And it's one of those things where it's my own thing. So if I buy 10, I am responsible for 10. Anyway, all that kind of stuff worked. Now we received the board, so let's just go through the unboxing experience, and we'll take it from there. So I'll be with you in 2 minutes. I just received that board now, and I've not opened it yet. I'm just gonna see what it's like. So this is the box from JLC. I hope it's kind of looking forward to that. So I've not opened it yet. Just remove my stickers. One thing I didn't like about this, I mean, I paid nearly, I would honestly say, about £3,000 so far on in stuff and redesigning and everything. And what I didn't like about this so far is, as I received the box, as you can see, ICOD paid. I was charged with customs for £250. Even though I'm a business, I can claim that back. But you see, I wasn't expecting that from from that side. So it's okay. But I overall was not singing and dancing about it. So I don't know what's in the box yet. Call it the unboxing of stuff. Yes, that's the order number. Blah blah blah. Stuff. So far, looking good. So that's nicely wrapped. Put that aside. Yeah. So this is as they done it from the other side. I am hoping it's a good thing. So that's the Omap design that I've been kind of wanting to complete for ages. It's 3 months now, and now it's just complete. Right. Well, so I've ordered a let's just go down to what we did. So these are the additional ones I've ordered, because these I'm going to use to be placed onto the this bit here, this guy. So just put them there for now. And this bit is the assembled one. These are kind of an additional thing. And here's my board. For the first time, woohoo! I got my board up. And things they couldn't do, things like the MIDI, they couldn't place in here because for some reason they got it wrong. You got the ESP32 nicely placed. The Omap chip is nicely done. And the stuff upside down, really nice. So to be honest with you, and the SD card. So to be honest with you, all the pain, I think, is now gone away from my head. I got my board. I got a working board. So I can't wait to try that out, to be honest with you. So the USB host, see, that's something I'm not happy about, because that should be to that side. I'm thinking Can I cut? That's probably I can cut, isn't it? That is yeah, that is something I can bend and cut, so that's fine. Sorry. And this one also, but I'm not gonna cut it yet because I need to. But the fiducia shouldn't be here. It should be outside somewhere else. Yeah, I'll check my design anyway. But yeah, that looks good. I am quite pleased that the system is there. At the moment, the quality looks amazing. It really does. Obviously, the board itself is beautiful, from a design from JLC work, but from JLCPCBA, mixed feelings. So now I have to place the header bit here and there, and the MIDI here and there. So that's something I'm going to have to do, which I'm fine with. I don't mind. But mainly, I wanted to get the Omap, the memory and the flash all placed up nicely here, and that looks pretty good. So I'm gonna so one more thing, by the way, they could not place the 2068, which is this chip here, correctly. I don't know. I need to look into using the microscope, and then we'll find out what it looks like. But they did say it's not going to be any shorts in there, so hopefully we'll see how that's going to go. So I'll carry on this video very, very soon. But that looks, to me, honestly, really, really good. I'm quite pleased. And this is the encoder, so you can just rotate and do menu settings and things. Yeah, so this is if this works fine, it's going to be the beginning of my new era, the Omap stuff and the music instrument making. So that's beautiful. Thank you. In a bit. Right. Okay. So just getting the board to be checked out to see what defects or possible defects we might have. So I'm just putting that there on the microscope. First things first, let's just jump on to the quality of the work. And as you can see in here, the board looks pretty stunning, to be honest with you. I like how it looks. So just gonna quickly, jump onto the microscopic side and see how things look down. So basically, we'll start from the power side. So you got on here, this section is the power, and basically got the 2087 chip. This is the splitter. So you got multiple USB ports coming in, distributed to one chip in here, and that then gives you a big power rail, the 5 volts there, and then that gives it down to the 2086 there. That one here, that's a distribution. That's the only one that I am aware of, but it looks absolutely fine, because look at this, the issue we have in here, you see that chip looks a little bit bigger than, sorry, let's just take it to a microscopic level so you can see what I'm talking about there. So let's just go back again on this. So yeah, power 2087 chip comes in, takes all the USBs, and then let's just focus that up. Yeah, okay, and that gives it to the 2068 chip, and that here, I was talking about that, so you can see if I zoom onto it, the work, you might think it is too little or too touching, but it's fine. The reason for that is because you can see that pin 2 and 3 there, the middle pins, they are the same connection, and 1 and 4, 1 is unconnected, and 4 is the one that takes the power and the signal out. And you got the bottom side of it is a big ground, so that's fine. Similar to this thing here, so you got the 1, 2, and 3 pins in here, or 4, 5, and 6. They're connected, and the last one is just it's not connected as well. So here, that should be absolutely fine. I'm happy with that, don't mind. And now you have here, this is the big one. I love this chip. This basically is the the power distribution. So what that means is when you get the power in here, this will give you a distributed 1.8, 3.35 volts, all from that chip. So this is basically, and it does it in a sequence, and that's the beauty of it. So there's few of them. I just love Texas Instrument for that stuff. So the power, it'll power up the rail based on what Omap needs. So it doesn't, it's not gonna take the power and then shoot it all up. It'll just do it in sequence where, as recommended for the Omap to power up, it will say I'm gonna start, for example, the 3.3 volts. Sorry, it'll start, for example, the base core. So the 1.2 starts first, then the 1.3, then the 3.3 volts, then the big CPU, which is 3.3 and then 5 volts distributed. So make sure that Omap is actually safe to power up and start. So that's a good thing. Quality wise, this is all fine. You got the power sensing resistors in here. So this is for me to find out, are we do have a short, shut it down and stuff, etc., etc. The quality so far looks absolutely amazing. I love what they did. In here you've got the flash memory there, and in here you got the SD-RAM, and here is the Omap itself. You can see, this is my finger, how small the Omap is. So you can see this is the I'm using the Easy CE, which is a 30mm chip. In here you got the host, a USB, and just forget about that. That's fine. Yeah, and now we are jumping onto the audio section. So basically here, these are the audio pins, and you got here the AD9851 chip, which is equivalent to the 793, and this is the 1802. That's the PCM input chip. So basically, we take power, audio in to the Omap. These connections in here basically means the configuration to power up, to tell this chip what to do, i.e. what sort of media, what sort of things to actually come up with. That here is the JTAG port, JTAG connection. You can plug in a JTAG and life should be should be nice. In here, this is where the chip will want to speak to the CPU. So I did not really connect it, and this is the beauty of it. That's why that's why I designed this board. So things like that. So this will not be directly connected to the CPU or to the Omap straight out of the box. To connect it, you'll have to use a jumper cable. So it goes from here and then into things like that, like the other side, or sorry, just to patch it up. So for example, you can put it there and then say to pin 17, do stuff and carry on. That's the idea of it. Now carrying on, you got the connectors. To be honest with you, the connectors and other things like that, I think they've probably been done by hand or something, because it's not really straight. They don't look like they've been machined in, but I mean, that's understandable. It's a little bit twisted, fine, no problem. Some bits in here unclean, that's not a problem. That clearly here, you can see that one also twisted. It's not really lined up correctly, but it's okay. And moving on, you've got the 3106. That's the audio chip in case you like to develop with an existing or the Texas Instrument default development board. You got it there as well. So the 3106 is there, and that chip is the difference from this one to the PCM. These chips over there is that this one will have a built-in equalizer, built-in bass, treble stuff, which is nice. It's fully configurable, unlike what's on the audio instruments. Whereas the audio instruments will have a pre-configured chip. There's nothing to do unless you do it by the Omap. So good and bad, to be honest with you. It's not a big deal. And also modes, configuration, things like that. You've got switches in here, so in case you want to do do things like multi-function. If you want to work on the audio instrument side, and this is the encoder, chip, the encoder thing. You can connect that down, and then from here you can just what you want to do with it. And here is the boot switch, where you select what sort of type of boot the Omap should do. In here, more modes configuration. The audio looks all good in here, so I'm happy with that. At the time, you might wonder why yellow. Yellow usually used for video stuff, but because we could not find red and white at the time, so we used yellows. But they're the same pretty much. They look good. And here MIDI, they could not fit the MIDI for some reason, so they said we can't do it. So I said fine. After months and months of waiting and things, I just got quite fed up. So I said fine, send me the board. I will buy the MIDI and do it later on. And here you have the ESP32 section of it. That's what's going to control the Omap to do more sounds and things like that. So that's something in the design. So what you have in here, you can do this and connect it to the Omap section, and then you carry on. Also, you have in here this little, that's an LED, an RGB type LED, so you can just do, more tests and things. You're going to do a light cluster and things. And also, these are all, you've got more RGB LEDs on that section as well. So it should be here, 4 of them. So there we go, RGB 1, 2, 3, 4. So 4 LEDs in there per design. Now, also you have the latest and greatest, what's it called, the chipsets in here, which is, there we go. So the TAA 5242 and the TAD 5242. So this is the audio input chip, the latest and greatest from Texas Instruments, which supersedes the 1802. And also you have the TAD 5242D, which is basically here, that's the audio output chip. So these two chips kind of the latest and supersedes the one used by other instruments. So this should be more powerful, more channels and more things, etc. Now we go back into a slightly higher level. So let's just switch the camera there and explain here. So you see in that section you got loads of header pins, and this is why I developed this, another reason, because that now is like an Arduino chip. So you've got all these pins representing what's on the Omap in here. And what happens is you can plug in anything you like, as long as you know what you're doing. You plug in the connection from that section to say I want to plug it into either to the ESP or to plug it to the audio or to the MIDI, do whatever you like. Also on the other side you have 2 more FTDI chips, which is for serial. So you can, let's just zoom onto those a bit, just cover those up. So you've got 2 serial chips for FTDI, token ring FTDI, that sort of thing. You can do a lot of stuff in there, and all the connections, you can see it there, so that's fine. Now on the back side of it, you've got some audio chips in here as well. And you got an SD card reader. Connection. SD card, not reader, it's a read writer. And so basically you can boot from that in the same way that you boot from any other thing. And here you got oscillator chip. That's 24 megahertz, and also you have another oscillator in here. So you've got 2 oscillators in case you want to back things up and do other stuff. So in a nutshell, that's what the chip does. Let's just carry on from the last bit. So now going into the power up of the chip. So let's just power this up and then see what happens. Out of the box, you shouldn't really attempt this because there's a lot of moving components in here, and just to power that up, we're not sure if it's going to blow up or it's going to power up fine. I'm just joking. Anyway, let's just power up now and see what happens. So it should be a light, and in here it looks like we are not seeing any light at the moment. So let's just switch this off. There is a light, but it's a bit dim. It's not really, it's not great. So let's just turn this one off too, and just focus on that one. You see there's a light there, but the problem, if I I can sense heat on that chip. There we go. So let's find out what is wrong. And so I'm using my thermal. So just gonna zoom out a little bit and just show you what's happening on here. So here you see there's a thermal on that section. So here, yeah, that's quite hot. And there's something not right in there, so we need to find out what it is. And you can see that light is flickering down there, which isn't right. So anyway, let's figure this one out. So when that heats up, it means that there's something shorted inside, and something isn't really right. So let's just disconnect this first. All right, and then do some tuning, because if the lights are coming up fine, it means there is power going in, but then because they're flickering, it means the system's trying to power up, thinking, oh, I can't do it, and then shuts down again, and then keep repeating the cycle until either that shortage clears or or the board blows up, or something blows up inside. So put it this way, the chips are getting heated up here and they're shifting the power up. It's a good thing, it's not a bad thing. It just means that it is working. It's just not able to power up the other stuff. So we're going to just measure stuff up and then find out what is happening. So just going to get my voltmeter and connect it to so you got the ground pin on green. So let's just take it here. So this is one of the nice things I've actually designed in here. Let's just take it to microscope level. So if you look at this, that's one of the things I designed to develop to debug what's going on. So ground goes here, and now let's just test the 5 volts. So you're going to put that there onto the 5 volts. So you got 5 volts USB. So let's just point these out. So you've got 5 volt USBs and 5 volts main. Everything should be powered up by main, but USBs is what this one goes into the main 2068 chip. Power and sorry, the 65 here, that one. So this one takes the main, USBs, and then fire out the mains. So it's like a big power rail. So 5 volt USBs goes into this chip, and then that distributes everything out. So it gives you then a main voltage. And then these 3.3 and 1.8, these are all part of what that will give you. So it's a nice way of finding out, do we have good rail or not? So we're going to take it to the 5 volt USBs. Get my voltmeter down here so you can all see it. Let's see what's happening in there. Hopefully you can see it. So let's just switch the cameras. And now you should be able to see what is happening. So yeah, I think that's good. You can see it there. Perfect. So also just thinking, let's just carry on with the standard USB. So if I plug this in, I should get a 5 volts. See that? I got 4.8. It's not quite 5. It's fine. Not a big deal. And now what we're going to do, we're going to find out which rail isn't really working. So we're going to take that down here, put it to the mains, and we should have the same 5 volts. And look at that, it's actually 2.3. So definitely something is shorted, something isn't really right there. Take it down and find out, do we have 3.3 volts in here? No, we have 1.9. So definitely that 3.3 isn't right. Something wrong with the 3.3 volts. And the 1B8, you got 1.7, yeah, 1.8, 1.7, that's fine. But that should be 1.8 if everything else is looking good. But it looks like there's a short and that's being pumped up. You can see the numbers moving, dancing on there. So that means there's a short on the 3.3 likely. 1B3 in here, and you got 1.2 and dancing again, which means there's something on and off. The 1.8 VLLDO, 1.7, fine. And then 1V2, yeah, 1.1. Okay, so I get an idea where things are, going wrong. So just take this off. So we're going to remove that battery. And now the other bit I have designed is now we can just going to switch on the lab power supply, and I'm going to start testing each connection. So I'm going to do a 5 volts, push a 5 volts in here and see what comes out. So keeping that there, so I'm going to look at the focus on the 3.3 like this. So now we are pretty much focusing on the 3.3 volts there. You can see it now, hopefully. And so ground and 3.3 are connected on that side. And also for the power supply for the lab, I'm going to push in a so we've got another, so we've got here 5 volts USBs there. So this is equivalent to USB power up. And now we need the ground, so I'm going to hook this up to the ground pin. Let's just replace that green with that ground. That's nicer, more darker. And yeah, so now this one I want you to go into that. So okay, so now we have the lab power supply connected. Now we're going to power up 5 volts with 1 amp. Go ahead. So 5 volts, I'm now getting 2.3 out of it. I do see lights, you can see that there, but it's not, it's not ideal. There's something not right. So 5 volts, USB's coming in, but 3.3 isn't working. And just before we carry on, another test we need to do, just to make sure that the power rails are all good. So on the power supply, let's take the voltmeter away. I don't need this anymore. And on the power supply, I will be testing each pin on that section separate individually. So the voltmeter is it's out of the way. What we'll do, using the power supply lab, I will power up this individual. So I can do the 3.3. So I'm going to lower up the power lab to 3.3 volts and then power up now. And you can see on here, you can't see it, but there's a short. I can see it on the power supply. The 3.3 is definitely shorted. So I'm going to power that off. Let me see if I can show you that anyway. So if I do this, and let's use this camera to record this just in case. Hold on. So what I have in here is I've connected the 3.3 volts to my lab power supply, and the lab power supply, you can see it down there. So if I power that up, you can see red on that section, which means that is a shorted and it's taken the whole 1 amp there. So we know that 3.3 is shorted. Testing the other ones. So if I go into here and switch this down to the 1.8 volt to see does the 1.8 is shorted. So take that power down to 1.8 like this, power that up, and that looks good. It's taken 250 milliamps. Still big, but okay. It's not a problem. But it's not shorted, so you don't have that red. 1.3 volts. You have to be really careful, and the volt has to be exactly right, otherwise the Omap will be fried. So 1.3, that looks good. It's taken 10 milliamps, which is fine. Power down. And the LDO side, the 1.1 V8 LDO there, should look also good, 1.8, because that's sourced from the other section. So yeah, that's taken almost nothing, but it's powered up, no green, good. You can see that there, green, almost no power wasted, so that's fine. And yeah, so clearly the 3V3 in here is what the problem is. So as we go in here, fine, so all that stuff is powering up nicely. The other bits, so if I take you there, so if I look at the system, you can see there's two things heating up there. You can see it on on the other side. So if I just take you there, you can see, notice, so that chip is hot. We know it's hot because it's keep powering up and shutting down. But the other side, look at that. So you got another bit, which is that one. And that is quite hot. Yeah, I can really feel it hot. So that here is the other chip that we need to investigate. So looking into further into this, let's just take this down. Sorry, I'm just going to power this on. Yeah, power off, good. Okay, so now we know something wrong on this chip in here. And now we're going to find out. So I'm going to power this off and just come down a bit into this section. And that here is the 4N35EN. Take you down there, and this here is the 4N35 chip. Just going to kind of try to focus it here to zoom in on more of it. So there we go, that's the 4N35. That chip is the Opto-Coupler, and that is used for MIDI. Okay, so we are down into the design phase and just trying to look into what is going on there. The chip we looked at earlier on was heated up from that side, and I think that's the chip itself. So if I look into, just zoom onto that. Wow, that's really raining outside. That's fine. Yeah, so that's where the chip, I believe, that was heating up, and this is the U3 chip. And looking at this, it looks like, just let me take that copper area off just to see it. Yeah, I think that's the one. It's the U3 chip, and I think I know the problem. So if I look into the design, it is definitely the MIDI. Yeah, okay. That's the U3 chip in here. That's the Opto-Coupler. Okay. I think I see the problem straight away. I don't know how I missed this, but anyway. Okay, an Opto-Coupler device is a device that as you have push input to it, you want to isolate your input side from your board side. So you don't want basically someone to connect high voltage and then burn your stuff up from a MIDI controller. So what you do, the MIDI in connection goes into a Opto-Coupler, whereas this diode there. So imagine this is when you have a signal that will light up inside the chip, and as it lights up, it'll enable that circuit, and that circuit will kind of push things out, and you have an output there. So straight away the problem is this, that should be firing to enable that base, to enable that connection. And in essence, what I'm doing, I'm actually overriding that. I'm forcing it with a 3.3 volt in here straight to the chip, which is wrong. So that that resistor should be here to isolate 3.3 going to the chip. Second of all, that is an NPN type, so that ground should come here, not there. Anyways, I don't know how I missed this. Anyway, looks like yeah, it's a bad, or missed it. I probably was drinking something. Anyway, so the solution is very simple, really, but it's not too late. I can take the chip out and then kind of wire something else in. It's not a big problem. So let's kind of fix this. So that has to come here clearly. So that ground comes in here, and now the 5. Yeah, that should not be connected anyway, because that's going to be powered up by that side. So we'll disconnect that here, and that 3v3 should go to the resistor first. Hold on. let's take this off. Take this here. Yeah. And that's not going to got yellow anymore, so that here goes. Yeah. So yeah. Yeah, that's how it should be. So the 3v3 gets into the resistor first and then hits the chip, and that's the signal in here. And whenever this guy comes in, it's a pull-up style connection. So what happens is it'll be on until someone powers something up, and this will be down. So yeah, I mean, can't believe I missed this. Yeah, so that's where the problem is, and the solution to the production design literally is just to kind of take the chip out for now and then think of something else for now. So MIDI in will be disabled on this design, unfortunately, until I figure out a way to place the chip back in again, and you know. So what we're going to do, we're going to take that chip off, the 4M35, which is the Opto-Coupler, and then take it from there. So removing all the wires from thingy and power that on and off, we're all good. Need to be really careful in here. So now the problem we have, just flip this upside down. The problem with this chip is because we are close to all plastics in here, so very, inside. It's hard to use, or it's definitely don't use a hot air to remove this stuff. It's not going to work. You're going to end up ruining so many things and causing problems. The best way to do, I'll show you that now. So what I'll do, I'll put some flux, or not flux, just, I'll put some flux there, why not? So flux on the pins in here. And what we will do instead is put some solder in, put a big blob of solder, and because the solder will be touching all pins, then when I heat it up, everything should come off easily. So that's the plan. And so we'll do that now. So I'm going to start with this, heating up to 400. And I will actually turn it the other way around because I don't want to damage the other side. So I'm good here. Right, so I'm being really careful not to touch any plastic. At the same time, I want to put that big blob of solder in there. Good. Same thing in here. Good, so there we go. So now we have the two bits covered with solder. Perfect. I'm going to use another soldering iron as well. And let's see if we can do this way. Yep, almost there. Yep, nearly there, coming off. Yeah, that's good. Okay, so we are lifting. I just need to use the tweezers now to pick it up. looks good. Yeah, looking good. There we go. It's out. Perfect. See that? With minimum damage possible. So you can see that the chip is out. We're not done yet. We need to kind of clear this off. So easily I will use my suction to take things in. Or actually I can wick it. Let's just wick it anyway. I'll use the solder wick here. There we go. So we're taking that out, that looks good. Same thing in here. Come on. Yeah, to be honest, I'm happy with that, but I'll just take more off anyway. Yeah. So yeah, I mean, that looks fine to me, but I still wanna do perfection. Yeah, that looks fine. Good. Other side. There we go. Nice and clean. Look at that. See? Good. Then, to be honest, with the least damage possible. In fact, there's no damage whatsoever. And I'm happy with that. So now, we just clean off the stuff using ISO. I'll use tissue. Yep, that looks almost there. Perfect. That looks really good. Just cleaning up, making sure everything looks fine. And that does. Perfect. So now the stuff is out and we are ready to do another test. So let's fire up the same things we did before. Now we're going to engage. So let's just make sure that we have this cleaned up. So we've got a little tiny thing. I can just do this to it. Done. And do that. That's cleaned. Just being perfectionist in here. That's done. And that's done. That connector looks fine. Slightly down there.
take it out. Good. And do that. And that. Just, you know, on the plastic side, that's it. Right, so now let's power up this stuff. So that looks all perfect for me, to be honest with you. Nothing wrong, it all looks good. Yep, and we're just gonna power up the 3.3 rail, same way. So I'm taking the rail here, good. And we'll use the plus for the 5 volt main, sorry, the 5 volt USBs, and this one for the negative. And take the same camera, and yeah, let's just connect the voltmeter whilst we're at it, just in case. So I'm going to connect the voltmeter to the ground on that pin, and this one we're going to put this on there. Yeah, I'll just keep this separately here just for a minute. Not going to power up the voltmeter yet. And we'll do we'll do a 3.3. So let's just take that camera here. We'll do a 3.3 now. 1 amp is fine. And I'm going to make sure that we are on the 3.3 rail. So there. So 3.3 and then ground. And here 3.3. Let's just power up. And look at that. That looks taken 70 milliamps and green. Looking all good. And the board is now coming up. So I'm actually loving that. So it looks like the short is caused by the wiring of the Opto-Coupler in there. Brilliant. So power that down. And we're going to now switch to 5 volts instead. And see if the 5 volts has a problem anymore. So moving to the 5 volts there, USBs, and this time I'm going to measure the 3.3 output on here. So now we have 0 volts on the voltmeter. We're going to push 5 volts, 1 amp, and then see. So 5 volts are in, no red, which means no circuit break, no short. And it's taking 120 milliamps, and we got 3.3 or 3.4 on the voltmeter. So that's brilliant, and you've got all the lights coming up. I am loving this. So now let's just do the testing. So we got the 3.3 is coming up nicely good. You've got the 1V8 of 1.8 volts, and that looks fine. 1.9, so it's okay. 1.8, 1.9 is not a problem. That's good. And in here 1.3. You got 1.4, also good. And 1V8 LDO, 1.9, good. And 1V2 is 1.3, also good. And 1V2 and 1V3, very good. So to be honest, the board looks up and running, and it's all pretty working. And now it should be, the Omap is powered up, everything looks good. I am, kind of excited. I'm really happy. So I'm going to power off the lab power supply, turn this off, remove all these connections, actually keep the voltmeter there, but I'm going to take this one off. Don't need it anymore. This one, hold on, let's just take this off from here. Put this down there just to measure the stuff. Make sure we're connected there. Good. Okay, so now we're connected. This time we're going back to use a USB cable. This is a battery here. And we'll test. Let me just put this camera aside. Can't keep holding it. Yeah, so we're going to test it now with this, and we should see a happy ending. Look at that. So yeah, I am really happy. Everything is powered up nicely, and yeah, so that's I can't believe it. I've got my board up and running, and the fault restored. I mean, it's not just a bit, not happy about the Opto-Coupler for the MIDI in section. But that's fine, I can live without it for now, until I either get a replacement or do something on the board else to get this in. But now, the board is working, and I'm really happy about that. So I really can't wait to, to come up with, or to do more work. And this is going to be the open source that I talked about earlier, and that's going to be ready, available for everyone to test. And once we're done with this, and once whoever wants to make their own instruments, then all we need to do is just do that section with the chips that for audio, whatever it is, and then the whole thing will be powered up by just that bit. So beautiful! I can't wait for that. So yeah, I think now this section of the project is now looking live, and the next videos coming up will be about what to program, how to test the other audio chips, and how to start seeing Hello World audio thing. So thank you for watching, and to be honest with you, I am really happy. I can't mention, or I can't express how happy I am, but I really am happy. It's like this is now coming to life. It's my baby. Yeah, can't wait to get this all powered up. So we'll see you soon. Thank you.